At this point, we know what field extensions are, and we know what automorphisms are. So what we want to do now is associate a collection of field automorphisms to a given field extension. So, given an extension, big K over little k, we'd like to associate a collection, a set, of automorphisms to that extension. And that set of automorphisms is going to be called aut of big K over little k. So let me first give the definition of this guy. Let me first define what aut of big K over little k is. And the definition is as follows. Let's let big K over little k be a field extension. Then we're going to write aut of big K over little k to be the set of automorphisms of k, the set of automorphisms of big K, which fix little k, which leave little k fixed. And remember, this just means that sigma of A is equal to A for all A inside of little k, or equivalently that sigma restricted to little k is equal to the identity. That's what it means when we say that sigma fixes little k. Okay, and in words, this set is often called the group of automorphisms of big K fixing little k, or the group of automorphisms of big K over little k. So I've already given away the punchline here, which is that this set, the setup here, this collection, or the set which we're calling aut of big K over little k, is not just a set, it's actually a group. It's a group of automorphisms. So this is a really important fact, because the fact that we have a group here will give us a lot of structure that can be exploited later on. So let me go ahead and write this as its own statement. It's so important that I'd like to write it again, in other words. So, fact. Just to repeat what we said above, if we have a field extension big K over little k, then the set of automorphisms of big K over little k, this set of automorphisms, this set aut of big K over little k, is not just a set, it's actually a group. So not just a set, it actually has the structure of a group. And the group operation is going to be functional composition. So to spell this out a little bit more thoroughly, what I mean is that if we have sigma and tau in aut of big K over little k, then the group multiplication, sigma times tau, is just sigma composed with tau. The identity element, as you can guess, is going to be the identity function. It's just the function which takes every element A to itself. And inverses are just functional inverses. So if sigma is inside of aut of big K over little k, the group inverse, sort of the formal group inverse, sigma inverse, is just the actual functional inverse. So it's the function that takes a given A to the unique B. It takes A to the unique B, such that sigma B is equal to A. Okay, so aut of big K over little k is a group, or so I claim. I'm not actually going to prove this. I'm not actually going to check that all of the group axioms are satisfied, but I do think this is something which everyone should see once in their life. So I encourage you to pause the video and quickly check that the group axioms are satisfied, and that this is actually true, that aut of big K over little k actually is a group. Okay. Now, before we go any further, I should just give you a heads up that this is going to be very important. It's really important to us, this object aut of big K over little k. It's kind of like the fundamental object in Galois theory, so we'll be seeing it a lot as time goes on. Alright, what I would like to do to finish up this video is actually consider two concrete examples. So, examples. I'd like to actually tell you what aut of big K over little k is for a couple of field extensions. So first, let's try to determine what aut of the real numbers over the rationals is. So we want to find the set of all automorphisms of R over Q. So we can give one immediately, right? The identity. The identity is an automorphism of R. It obviously leaves Q fixed, so the identity is an element in this automorphism group. And it turns out that the identity is actually the only element in this group. Now, that's not so easy to see, but I will post a detailed video giving a proof. So if you believe me that this is true, or if you watch the detailed video and see that it's true, we know that aut of R over Q is the trivial group. That's the trivial group, the trivial one element group. trivial one element group. Okay, now let's consider a second example, and that's going to be aught of C over R. So what elements are in this automorphism group? Well, again, we know that the identity is in there, right? The identity is always going to be in there. Every time we form aught of big K over little k, we'll always get the identity. We'll always get the identity morphism. We also know of another thing which is in here, which is complex conjugation. So complex conjugation is an automorphism of C, which leaves R fixed. So complex conjugation. Okay, and it turns out that these are actually the only automorphisms of C over R. Now again, that's not so easy to see immediately, but I'll put up a detailed video proving that that's true. So the only automorphisms of C over R, the only guys inside of this group, are 1 in complex conjugation. And well, there's only one group with 2 elements in it, so that means that aught of C over R is isomorphic to that group, that abstract group. So it's isomorphic to the cyclic group of order 2. And the isomorphism, of course, is going to be the one sending the identity element to 0. It's going to be sending complex conjugation to 1. That's what the isomorphism is. So aught of C over R is isomorphic to Z mod 2, and aught of R over Q is just the trivial group. And those are the 2 examples that I wanted to give. So to finish this video, let me just reiterate that aught of big K over little k is really important. So as a heads up, aught of big K over little k is really important to us. It's really important in Galois theory. So it's important to understand this guy. It's important to sort of know what this is, because it's kind of the fundamental object that we'll be dealing with in the rest of this course. So this is just a heads up that whenever I say something about this, it's likely that it'll come up again. For example, these guys are going to make up about 1/2 of the Galois correspondence. So remember, that's the correspondence which we're trying to define right now. That's the kind of really important object in elementary Galois theory, one of classical Galois correspondence. So these groups are of fundamental importance to us. Okay, so in the next video we'll be talking about the other half of the Galois correspondence, and those will be fixed fields. That's what we'll talk about next.